joining. And okay, and thanks for agreeing to be our monthly speakers. And thanks to Chris, who has introduced you to us. And I'm extremely impressed with your biodata and the kind of involvement you have started with India. Formally, for the audience, he's a professor in School of Engineering Technology at Purdue University, and Daniel C. Lewis, professor in the same Purdue Polytechnic. As I was reading his biodata, which is not in front of me, but I saw that he had Purdue, CMU, and Stanford, all best combinations. He has it in his credits. And then he's also head of collaborative robotics, which is our also the company is IHFC. So again, welcome to our monthly seminar series, and this is the 8th one since we started, and we were eager to hear from you, Richard. Hand over to you.
Excellent. Let me reshare here. There we go. Well, thank you. Thank you very much for allowing me this opportunity. Whoops, let me swap these. It's been great. Thanks to Krish and Navtat for inviting me in this part to be part of the Cobotics iHub. I think this is really an exciting opportunity, that's what I'm here to talk about today. Is a couple of projects actually that focus on the semi-autonomous robotic surgery, in particular teleoperation with delays. And this is a number of projects, again, that some sponsored by the U.S. Army, some with Amazon Research. Chris and I were actually trying to get some engagement with L&T Technology. Again, I'm going to say a little bit because I've been doing a number of visits and interactions with universities in India, and particularly been working with Krish in the past with PSG College of Technology in Coimbatore. I'm excited for this opportunity to work with IIT Delhi. Again, this is a collaborative project. The U.S. Army grant is actually led by Professor Wachs. The Amazon Research work we're doing is led by myself. We also have Professor Yizhang Zhu, who is a professor in computer science. Dr. Wachs and Dr. Agarwal are both from industrial engineering. But let me go on and talk that, we know the story about minimally invasive surgery and laparoscopic surgery in particular, how it's really reduced trauma and collateral damage to the human body. There are a number of benefits to minimally invasive surgery in general that include reduced infection and pain. There's also shortens recovery times. There's much less a risk of addiction to painkillers. Opioids in particular is a big problem in the United States. With laparoscopic surgery in general, there are over 15 million operations now globally. It's really been a growth area in surgery for all these benefits. And of course, at the same time, robotic surgery as a subset of these laparoscopic surgeries has been growing also at an exponential rate. This is the Da Vinci surgical robot. There are about 2,800 installations of these robots in the US alone right now. It's a $4 billion industry and growing at about 10 to 15% per year. And it involves a number of benefits that particularly for the ergonomics for the surgeons, it gets them away from x-rays and real-time imagery, which can improve surgery. It presents doctors with a much more ergonomic environment, especially for long duration surgeries. It allows collaboration. And of course, the idea of surgery by wire has long held the promise, particularly for rural environments where there aren't as strong medical and surgical surgical expertise and equipment, that having remotizable surgery we can see these two surgeons working as well as a nurse practitioner in a concerted effort. And, this can really revolutionize healthcare in rural areas, and this is one of the main benefits for the Robotic eye hub here in India is for this benefit of remotized surgery, getting experts where they need to be, so you don't have to have all these highly trained and constrained surgeons everywhere throughout the country or the world, for that matter. The problem is that ideal has not really manifested itself, because right now all these surgeries are done with the doctor just like this, or at least very close. And that is because of, even though there are some benefits, the cost is very high. The Da Vinci cost anywhere from $500,000 to $2.5 million, and that's just the initial cost. Then there's $80,000 to $170,000, and these are U.S. prices at least. That $80,000 to $170,000 per year just for maintenance. And so and ironically, the Intuitive Surgical was actually initially funded by the U.S. Army in exactly this kind of a scenario, where if we have that austere environments on the battlefield, they really wanted to get remote surgical care because, medics and it's a very difficult environment. They're often targets in wartime, and it's these austere environments which don't provide good internet and network coverage. It's very difficult. And so the idea behind the Forward project that we are getting funded as, which also was the original funding for Intuitive Surgical, is this idea that if we could have robotic litters, robots that could then provide this remote assistance, so surgeons could be out of harm's way, or medics for that matter, and could give direct care, at least to save life, to stabilize a patient while while they get transported out of the battlefield zone. And so the problem, however, in these austere environments, again, whether it's the battlefield or whether it's a rural doctor's office or hospital room, that often these are network constrained. And the risk of having direct teleoperation is just too high, right? If we have potential for delays in data. And so what our approach has been, as well as many, is to look at having the remote surgeon not actually directly teleoperating and controlling the robot directly, but working on a virtualized reality, a simulation. And then that minimizes the data throughput, so that the understanding basically of the operator isn't seeing basically the whole data transfer, which it can be megabytes per second, and getting all the surgical information. And in fact, generally that involves stereo vision, and it's increasingly involving haptic and tactile sensing, the whole state of the machine, and which is often a multi-arm situation, as we saw with the Da Vinci. And there are a number of competitors, of course, with the Da Vinci. L&T, for example, has trainers for surgical operations, and that's part of what the iHub is focused on, is operationalizing robots such as that. There are open source and a number of other companies that are trying to reduce the data, but the fundamental thing that's missing for rural care is this reduction in data and the ability to have autonomy if the robot needs to take over and complete a critical life, a life critical step of the operation, and you get a network lag, it's absolutely critical that the robot can run, then take over full autonomy and at least complete the task. And so that is what this project is about, and how we're using basically simulation as the intermediary, coupled with machine learning of the operations involved, which these critical skills involved are what we refer to as surgemes, and what the community refers to as surgemes. These skills involved, which we see on the left. Pardon me, we have a total of about 11 surgemes that our system is capable of doing, is capable of learning and has recognized. And then we have these basic operations, some in training. We use the standard skill transfer task, PEG transfer task as a skill learning for training approach. And then we have a couple critical aspects of the military interest. Again, their interest primarily in stabilizing life to get them to a more secure location. So debridement, the removal of life-threatening damage to the skin, burns, that sort of thing, is an important task that the U.S. Army wants to see. And then also cricothyroidotomy, which is basically similar to a tracheotomy. It's breaching an obstruction in the airway in a critical, again, there's one of these critical life-saving operations you may want to perform on the battlefield immediately if a person is losing blood, is unable to breathe. Get these quick type of operations underway while they're basically in transport. So the envisioning of these systems is an automated litter would protect the wounded and provide this environment that could allow the remote surgeon to operate while the wounded person is being brought in. And so here's what we have is on the operator side, again, the surgeon is operating through a virtualized reality. So it's a simulator with the realistic imagery added, imagery and control added from the robot. But again, it's not the full video stream, which requires very high bandwidth, very high quality communications network. It's working and then sending commands through in terms of these surgemes, which again are autonomous execution units that can operate. And the whole time it's providing pass-through teleoperation. So if the network is working fine, the surgeon is in complete control, although they're operating on the virtualized reality in the simulation. They're in complete control of the robot, yet all the while the robot is learning, observing what the human is doing, extracting those basic surgemes and transferring that low bandwidth data over to the operator, or the operation unit, the robot, which is then operating these, or executing these surgemes in real time. And again, providing elements of that feedback so the operator, the surgeon, can see what's going on. Now, I'm not going to spend too much time on the surgical training. Again, this is the PEG transfer task. And it uses a subset of, so this is a classic peg and pull. What I really want to talk about is one of the opportunities here is for transfer learning. And so we've done a number of explorations in using trained operators. And I should back up and say the surgemes are trained offline through practice and training. And this involves both direct teleoperation of a number of different robots, and this is an example of the robots we're working with currently. And also because training time is also valuable, we're actually able to transfer skills between robot setups, as well as either direct teleoperation, where we have, you can see the Taurus Robot, which is an SRI robot that is designed for surgery and is a very small, compared to the Da Vinci, which is on the far right. You know, it's a very small setup appropriate for the U.S. Army's needs. And we also have a simulator for the Taurus. And we can work either with the robot in reality or the robot in simulation for, and we've demonstrated, again, these transfer learning from one machine to another, bootstrapping prior knowledge across these platforms. The Yumi is an ABB industrial robot, bimanual, very much like the Taurus, although it has slightly different kinematics, and we've adapted that both for the Yumi robot itself and the simulator. And finally, we also have a Da Vinci. We got one of their research manipulators, which are basically repurposed older versions of the surgical robot, which we now have, which we're porting all our systems to, and don't yet have a simulator for the Da Vinci. But that's what these things are doing, is through this process of learning during training, we develop these surgeme skills, and then we're actually able to transfer them and bootstrap that learning across all these platforms, minimizing the total amount of training time on each robot. Again, these are, you know, some examples using the training and on a sequence-wise and frame-wise basis for just a simple training peg transfer task. Again, these are, we're seeing some very high accuracies as they're transferred. I'm not going to go too much into detail because I want to talk about some of the actual approaches in debridement. And so this is, the debridement task has a slightly different set of surgemes. Again, the approach, the align and grasp are similar. Cut is a little bit unique here and is different from an incision. We'll see that with the Craig task. But let me show, I'm going to have to switch here, if you'll pardon me, just to quickly show the video. Here is, now this is simulated. So these are simulated skin and simulated wounds. And again, this is a procedure where an operator is doing this via teleoperation. And again, so the operator is in complete control at this point. And demonstrating the task, and the oops, let me see. Pardon me, let me back up. Whoops, got the wrong. Oops, okay, I'm sorry. Restart my. There it is. Get back. Sorry about that. I am didn't have the video for the from the simulator's perspective, but what we're using basically is, so our learning approach is an LSTM based long short-term memory based approach to determine the observation of the task being performed, and then is extracting again the probabilities of the appropriate surgeme in real time to transmit those to the actual operation, and which is again being represented both in the simulator to that the surgeon is essentially operating, and at the same time is doing this task on the real robot. And so this is our current level of training. This is this is an example of the transfer learning task, where, and this is only one subject, but 12 trials. We're still in testing phase for debridement. We did most of our development has been on the peg and pole task for training, and we're still doing 2 more subjects trials. And what this is showing is this is the raw learning of the various surgemes, and then compared to when we use multiple components from the different, both not just from the Taurus robot, but from the simulator and from our UMI tests as well. And then finally, I wanted to talk about this, the Crike task, where again, this is going to be also in simulation, but these are establishing, actual incision-based tasks. And the again, Crike is showing. Oops, I'm sorry, I haven't switched displays. There we go. I'm going to have to switch back to show the video again. But so the Crike is a task that involves palpation. So a surgeon or a medic, when they're doing the task, actually has to find the location on the trachea in order to open up the airway. And so there are 2 things that are a little bit different here is the palpation, and of course that is finding the appropriate location to make the incision, and then of course the retraction, the actual incision itself, and then retracting the skin to actually insert the tube, and at this breathing tube, and so again, we're using, because the palpation requires additional tactile sensing. And so what we're using is yet an additional robot, which we call our Super Baxter, also a bimanual robot that is been fitted with the same pods, or at least grippers, and our little laparoscopic grippers that we use for both the Taurus and the UMI robot. This, of course, is the simulation, but these are based on 7 degree of freedom Sawyer arms, and it's a pair that we use for our co-robotics work in actually working, because it has a lot more force feedback and tactile information. So these have full wrist force sensors. There are additional force sensors built into our surgical instruments that give us both general force information and some tactile tip information, which allows us to do the actual Crike task. And we're using RGBD cameras in this case, as opposed to the passive stereo pair of the Da Vinci or the Taurus task. We're using RGBD depth cameras for understanding the 3-dimensional environment. And again, I'm going to, whoops, I want to show the Crike task, which I have to switch back again to, oops, where is there it is. Oh, sorry, I had it pulled up. Where is it now? Oh, I moved forward. This version. So here is, oh, I'm sorry. This is the demonstration for the But I wanted to show this video. So again, this is the robot actually doing the recognized palpation task. And so that's basically the force sensor, a tactile sensor that is doing the palpation to extract the location of the incision. And then this is the surgeme. There's the force. So both of these are force-driven tasks that actually does the palpation and incision of the and that was this is obviously a simulated skin section for the current state of our Cricothyroidotomy task. And the bottom line is we're incorporating both kinematic and force-based tasks into the operational environment for surgery. Let me swap back. All right. Again, this is then the final, as a final, I'm going to, and so the Cricothyroidotomy task, as I want to point out, goes up to the incision. We're still working on the surgemes for retraction and haven't yet provided that we can't do the full demonstration because of the skin retraction and insertion of the tube. But what we've been doing with, so the full tests we have under the current development is, as I mentioned, with the peg and pull transfer task, again for surgical training. And here we have the setup where the operator is using these Hydra virtual reality controllers to perform the surgery. The system is then presenting a, there we go. Suddenly my link is working now. It's performing the, here we go. So this is the operator then operating on the surgical environment. Here we see the view from the simulator, and this is the what the automated system is recognizing and doing prediction actually on surgemes. And then here we have in a simulated, this is just a pool of red liquid to simulate the monochromatic or more to eliminate the color issues of standard test. Makes it much more easy to see the pegs, and so we're just using this monochromatic scene, which is a little bit more difficult for the vision system to test. And the oops, now I'm going to have to swap back because this is my sorry, I have to keep doing this back and forth. But then the results, I'm going to finish up here then with the results from our, oops, why did I do that? Okay. And so we're looking at, pardon me, then we're under these tests using that setup with the peg and pull, we were actually injecting delays into the environment. And whoops, injecting these delays into the environment, and the system with we show here 0, 1 second, and 5 second delays, and then there's of course the baseline in direct teleoperation, basically above about 2.5 to 3 seconds of delays with direct teleoperation, the direct teleoperation becomes unusable. There are too many collisions, and the lack of control with direct teleoperation renders it basically unusable. With this through the simulator-based approach to surgery with surgemes, that we can see that basically up through 5 seconds of delay, there's very little degradation in the ability to succeed compared to, again, direct teleoperation. Beyond about 5 seconds, when we get up to about 7.5 to 9 seconds, then the remote surgical system becomes unworkable from a teleoperation perspective. And again, that's when autonomy can take over. But so there are basically 2 stages: just the reduction in the data throughput and semi-autonomy allows teleoperation to continue much later into the procedure. Again, we can tolerate up to about 7.5 seconds, which is about 3 times worse than direct teleoperation in terms of delays. And we have the ability for actual full autonomy, because the system is recognizing the actions that are being taken while the surgery is being undertaken, and then is again able to complete those operations autonomously and get through any critical periods that were life-saving or that are required for life-threatening potential problems. Now, again, if the surgery is in a state where there is no risk of life or criticality, then the surgery would not. It could wait. Again, if it's in a safe state, it can wait for the surgeon to regain control. And this is an important part of. I want to talk briefly about what we're doing in future work. Obviously, this is ongoing. We are still going through. The system is fully operational in training mode, and we've run these trials with multiple users in multiple trials. The extension to debridement task and the cricothyroidotomy are still undergoing. We're just entering testing. Again, we've done 1 subject testing on the debridement task, and we have 2 more subjects that are going through those. And we're just in the process of finishing up the surging training for the full cric task, the cricothyroidotomy. And we are not yet ready, but we're a few months away from doing subject testing on that. And as a final thing, this idea of coaching and extraction of style is an important part of what we're working on. And one of the things we want to bring to the iHub consortium is the actual extraction of style. Because surgeons while they're using the same procedures, they often operate with slightly different style. And if the robot is taking over and suddenly regains control, we want to make sure that the robot is exhibiting the stylistic differences that the surgeon is using, so that it's much more natural if it comes back to a point, if the network resumes performance, and the surgeon then, of course, to them, they're operating on the virtualized reality, and so they won't notice necessarily the difference. And so we want to make sure that those systems resync with precision, so you don't potentially cause more danger. And so that wraps up the work we've been doing, we have a number of publications in this area with some data sets that we've published on our surgical operations and the surgeons themselves, as well as explanations of different stages along the development pipeline. So with that, I thank you for your attention and welcome any questions if there's time. I know we took a little bit more than I was supposed to take. Apologies for the slow start.
Thank you, Richard. Yeah, we can have a couple of questions because we don't want to leave you alone without any questions. Yeah, audience first, if you wanted to have a question, please raise your hand or just.
Yes, I would request everyone to please raise their hand and we will sequentially. Yes, Sautrik, go on.
Hi, Richard, sir. Hi. Hello, can you hear me?
Hello, how you doing? Yes.
Go ahead.
Yeah, regarding that military remote operations which you talked about, you said that for a remote operation to take place, the commands from the command center has to reach that remote location for the operation to be successful, right?
Yes.
So my question was that this transmission of data packets is prone to man-in-the-middle attacks, right? And
Yes.
like security threats. So how has there been any research aimed at this area, or do you plan on doing so?
Yes, that's an excellent question, and there are. Let me just give a little bit of background in that the Forward project. There's a program that with the U.S. Army that we are have this one active grant on. That's again called Forward. That has kind of it's a holistic approach. That includes the work we're doing and a couple other projects, one of which is on cybersecurity. And so our part of this project, we have not focused on cybersecurity, where they've been, we're instructed to assume that we have a secure link. But we are doing some work in related. Again, I mentioned we have a couple other grants from Amazon Research, but also NSF on the CPS program, where we are looking at making use of the fact, since we know something a lot about, in the case of these surgeons, we actually know what we're transmitting and what they should look like, and so we're doing some real-time malware detection, basically semi-supervised learning approaches that, because of the risk of more, basically what we're looking at is for medical applications, for non-military applications, they require authentication. Whereas we're looking at authentication-free approaches for network security to detect malware before we execute it, and because we think that is in an IoT kind of framework, in industrial frameworks, there often isn't as much opportunity to authenticate directly with every individual device.
That makes sense. Thank you.
So any other question? Yeah.
Maybe this is the last one.
Yes, sir. Sir, my question is that a lot of times whenever doctors are working over operations, problem is seen that a lot of times the case is very much different because each and every person has a different body type, and the biology might change somewhat, like organs have a certain position. So how will you deal with such kind of problems?
Excellent. And that's really the essential nature of the stylistic approach and the that's intrinsic, it's built in essentially to our approach, because it is fully parameterized by the operation and by what the surgeon is doing. And so there is some, and it is a shared autonomy that's going on here, right? The robot is technically on the millisecond, or at least hundreds of millisecond level, is working autonomously, but it is carefully being overseen, right, in the sense of teleoperation by the surgeon. So it's constantly being reparametrized, and it is, but at the same time is making use of the learning. So these surgeons are developed over many people, many surgeons, right? The skills brought in through training, through actual operations, and it can continuously learn from new surgeries. And this is all being shared in a database, and this is why transfer learning is important here. All these different things amount to learning not only the basic operation, but the style and the perturbations for each individual patient and each individual surgeon. And so all those things are brought to bear. Eventually, we don't have the full stylization implemented at this point. We do have the framework, but right now we're not extracting the style, but it is parameterized to each specific patient and particular surgery being involved. Did that answer your question?
Yeah, should be. So, while Udayan, are you allowing Deepak?
Maybe if Deepak can have be brief about his question.
Yeah.
Yes.
Yeah,
Try to be quick. Yeah.
Yeah, hi, Professor. So my question is more in the context of Indian scenario where the population is huge and the experts are quite less, and it's quite difficult to cover such a population with less number of experts. Even in a teleoperated scenario, we need the involvement of the expert at some point of time, and there is a lot of infrastructure required for the communication to happen. So what do you think of increasing the autonomy one step further, like a fully autonomous system in such a scenarios? We understand the difficulty that the doctor has a lot of prior knowledge and skill to do that task. Can a robot become that much skilled to do that task?
Yes, that's essentially what we're working toward. This is a fully autonomous system. If you just now let me be clear what I mean by semi-autonomous. It's semi-autonomous in execution, provided that it's given a plan for the surgery. In the case of debridement or the Crike task, in the case of debridement, it would have to someone would have to point out the areas, and in other words, the system can't look at an entire body and figure out which are the critical burn areas. But if the critical burn areas are just approximately pointed out, it has the intelligence to localize on what is good tissue and what is damaged tissue and what is not damaged tissue, and do that kind of removal. And so these are fully autonomous, but it's just tightly tied with human in the loop control at the sub-second intervals. So if you just provide the plan ahead of time, that if you know you want to do a cricothyroidotomy, you can just say, okay, there's your patient, here's your alignment, go ahead and perform the Crike task. It can do it.
Yes, I got it, sir. Yeah, thank you.
Okay, so Udayan, you want to thank Prof?
Yeah. Thank you, Professor Richard Voyles, for your amazing presentation and lovely interaction with our audience. So I also had many questions, but because of time constraints,
Yeah.
we have to move forward.
Yeah.
I will
I
get back
also,
to you over emails.
yeah.